All right, so pages 20 and 21. I want you to look at 20 first. On 20, I don't remember the year I pulled this data. I really should start labeling things better. But on page 20, it's heights of all the shooting guards in the NBA in whatever year I pulled this data in. How many shooting guards were there at the time? 123. I want you to look down at the bottom of page 20. There's a dot plot, one dot for each of those 123 shooting guards. And so you can see the population distribution, and then there's some summary statistics off to the right-hand side. If I were to ask you to describe the shape of the population distribution of that dot plot, what would you tell me? Skewed left, yes. What is the mean of the population distribution? 76.333. What about the standard deviation? 1.673. Perfect. We are going to do some random sampling. You're going to need either the app on your phone or you're going to need one of the graphing calculators from the back. This first random sampling, you're going to do it 3 times over. How many shooting guards are you going to select for your random sample? 2, right here. You're going to do a random sample of 2. So random, no repeat, math, probability, random, no repeat. From 1 to what? 1 to 123, and you're going to have it choose 2 of the shooting guards. After you have it pick out those 2 shooting guards, you're going to go find them on that list. You're going to record their heights, and then you want to average that. How will you average those? Add them and divide by 2. You're going to do that a total of 3 times, and then you're going to come over here, and you're going to put a dot up on this top dot plot, 1 for each of your samples. So you're going to have 3 dots total. So while you are working on getting this dot plot copied into your notes, I want to look at our distribution, at our dot plot here. How would you describe its overall shape? I mean, I think it looks more normal than the population distribution. But I do notice, like, we've got this trailing tail over here. Like, most of the data is right here. There's a little tail over here, but that's about the span of my hand. Over here, we go out twice as far. So I do feel like it has a left tail to it. I would say that this one is skewed left, like the population distribution. And what we just drew is not a population distribution. Does anybody remember what we call this? It's a sampling distribution. We took samples, we found their average, we made 1 dot. We took a sample, we found its average, we made 1 dot. Sample, average, 1 dot. This is a sampling distribution of X bar. Where n equals 2. Each of our samples were of size 2. You might have to flip back in your notes for this one, but we know the mean of this sampling distribution. We shouldn't have to guess at it at all. We did this before break. We did this the Friday before break. So if you need to look back at page 18, you're more than welcome to how we should find the mean for our sampling distribution. Should be in the box up at the top of page 18. How do we find the mean for x bar? It's the same as the population mean, so it's the same as mu. So what would our mean be here? 76.333333. That is the mean of x. How are we supposed to calculate the standard deviation? This is also in that box on page 18. How do we calculate the standard deviation? Yep, we take the population standard deviation and we divide it by what? The square root of n. What is n here? 2. N is 2. So I want to do 1.673 divided by the square root of 2. And that gives us about what? About 0.183. What? 1.183, sorry. 1.183. Standard deviation got smaller because we have samples that are bigger than 1. What should we have checked before we actually calculated the standard deviation? 10% condition. Anytime we go to calculate standard deviation, you've got to check 10% condition. Is 2 less than or equal to 10% of all of my shooting guards? Yes, because how many shooting guards did we have? We had 123, so I'm going to write this off to the side just because this is probably one of the most forgotten pieces. We're going to check our 10% condition. 2 is less than or equal to 0.10 of 123. Check. Right. I want you guys, so that we have something to compare and contrast this with, I want you guys to do exactly what you did before, except I want your sample size to change. Last time we were doing samples of size 2. This time, I want you to take a random sample of 10 shooting guards. Do you have dots to put up?
I do.
Okay, give me just 1 second and I'll open it up and you can put them up there.
Gosh.
Right. You're going to do random samples of size 10. So from 1 to 123, you're going to choose 10 and then you're going to average those. And then you're going to come and you're going to put the dots up here on this bottom graph. So this is interesting. What happened? Yeah, put that into stats words. I liked that. The variability is lower. Why? Sample size got bigger, variability goes down. You're going to see it suck in on both sides. What's it getting closer to? It's getting closer to the center, which is going to be at 76.333. Let's go ahead and write down what we have here. We have another sampling distribution. Of x bar, this time n equals 10. Would you still describe this as skewed left? Sure. Like, I see a little tail over here, but I see a matching little tail on the other side. Doesn't look skewed left to me, not like this one up here. This one looks much more skewed left to me than the one that we just made. How do you think we would describe that shape? I would describe it as approximately normal. What do you think we would see? I'm not going to make you do this, but what do you think we would see if I had you guys do this again, but instead of n equals 10, I had you do n equals 20? it's going to get, the variability is going to get even smaller. It's going to get even tighter around that mean, and it's going to take on an even more approximately normal shape because we're getting closer and closer and closer from both ends to that population mean. Standard deviation. Before we can actually calculate the standard deviation, what do we need to check? 10% condition. Do we pass it this time? Barely, but yes. We have 10 is less than or equal to 0.10 of 123. What is 10% of 123? 12.3. And we have something smaller than 12.3, so we're good there. So how do you calculate the standard deviation now that we know that we can? Would it be the same as the other one? Is it still going to be 1.18? Yes, 1.673 over the square root of 10, which comes out to be about what? 0.529, 0.53 if I'm rounding it to two places. So we went from a population standard deviation of about 1.7, and then our first sampling distribution had a sampling distribution standard deviation of about 1.2, so it got smaller but not a ton. My n value got a good bit bigger. My standard deviation got quite a bit smaller. That's less than half of what it was when we had samples of size 2. This idea right here, what we saw happen in this graph, we call this the central limit theorem. Do you remember how when we did proportions, we had to check large counts? We had to check to make sure that we had at least 10 successes, at least 10 failures that were expected, and that's what meant our distribution was going to be approximately normal. Here, my population was not approximately normal. Friday before break, we looked at an approximately normal population, and the sampling distribution was approximately normal. Here, my population distribution was not approximately normal, it was skewed left. And when we did small samples, the sampling distribution was not approximately normal. But as our sample sizes got bigger, we became more approximately normal. I didn't make you guys do this, but to be on the safe side, what we check for with our central limit theorem, we want an n value of 30 or bigger. If I'd had you guys do samples of size 30, we'd have been here all day just adding those numbers together and dividing. So far, so good? So instead of having to check large counts, instead of doing n times p and n times 1 minus p, we just have to make sure that we have a sample that is at least 30 or larger. And then we get to assume normality for our sampling distribution, even if the population distribution is not approximately normal. All right, looking down at the bottom of the page, number 5. I want you to use a normal distribution. So that immediately means you need to do what? You're going to draw a picture. You're going to use a normal distribution to find the probability of taking a random sample of 30 shooting guards and getting a sample mean more than 77 inches. What is this 30 that they're giving us? That's n. That's our n value. So draw your picture. Other than your picture, you need 2 more pieces of information. What do you need? Mean, which is going to be 76.333, just like the population, and you'll still need to find the standard deviation. We have a different n value, so your standard deviation is going to be different. So you will have to calculate that. Good question. We're going to go ahead and do this one anyway as if it passes, just for practice doing normal distributions. Technically, if it fails 10% condition, you cannot calculate standard deviation using the formula because the formula depends on independence. If we were sampling with replacement, so the same shooting guard could be chosen more than once, then we're good and we don't have to check 10% at all. Same as this, same as this.
Okay.
Yep. Then after you have your mean and your standard deviation with your picture, you'll want to do normal CDF. Which way should your picture be shaded? To the right, because it says more than 77 inches. So your picture should look something like this. How do you calculate the standard deviation? Square root of n, which in this case our n value is how much? 30. So 1.673 divided by the square root of 30, which comes out to be about what? Yeah. About 0.305. And then we do a normal CDF. We want the probability that x bar is greater than 77. So we have a lower bound of 77 and upper bound of something stupid big. Mean of 76.333, standard deviation of 0.305. And we get about what? Yep, 0.014. So slightly less than 1.5%. What do you think would happen to this probability if that 30 went up to a 50? It's going to get smaller. My standard deviation is going to get smaller, and that's going to make my probability go down because it's going to make the distance, my 3 standard deviations out, it's going to be a lot less. All right, let's flip this over on the back side. Finish up in style. Only one big main point today, and that is the central limit theorem. Central limit theorem tells me as long as n is big enough, then we can assume normality. You have to actually go in and check this. So we have large counts for proportions to check for normality. When we're looking at means, I can't have successes and failures with means. A mean is an average. That's not a success or a failure. So when we're talking about means, I either have to know that my population is approximately normal, or if I don't know, or I know that it's not approximately normal, then I need to have at least 30 in my sample, 30 or more. I would like for you guys to do numbers 1, 2, and 3 on the check your understanding, and then we will come back together to compare your answers to mine. I'm going to give you about 5 minutes to work on those 3 questions. Bless you.
That has to go the same direction.
Oh, okay.
Because it's smaller than 13, but bigger than 12. There you go. Okay. And that looks perfect.
Mm-hmm.
You checked your 10% condition. Yep. So you have your mean and your standard deviation.
Mm-hmm.
Yeah, that's looking perfect.
For other words, which one to use for the solver? The equation of the
How did you say it was distributed?
Huh? It was.
We'll get there in just a second.
Even though we can't see it, describe to me the shape of the sampling distribution. It'd be approximately normal. Why? Because of the central limit theorem. The sample is bigger than 30, so the sampling distribution is large enough to use the central limit theorem. This is distributed normally. Without this information in number 1, you can't do number 3, because you wouldn't know which function to use in the calculator. You have to know the shape of the distribution, and you have to know that it's approximately normal, or else you can't calculate the probability down in number 3. What is the mean for this sampling distribution? 13.5, the same as the mean for the population. What do I need before I can calculate the standard deviation? Have to check your 10% condition. What am I checking with this 10% condition? Yes. 100 is less than or equal to 10% or 0.10 of all iPhone users, specifically all iPhone users who share their data with Apple. Because there might be iPhone users that aren't being taken into account here. They don't share their data with Apple, and so we don't have access to that information. If you just wrote down all iPhone users, that would be fine. I would accept that. Please make sure you're including all, though. It needs to say all iPhone users. What is the standard deviation here? 0.375, no rounding necessary. And so then your sketch should look like this. We're going to calculate the probability, which is the area right here between 12 and 13. So lower bound and upper bound are 12 and 13 with a mean of 13.5, standard deviation of 0.375. Normal CDF, since we know it is distributed normally. And you should get a value that is approximately 0.091, ballparkish. Kind of curious. The probability that the weekly screen time for the sample, not the average screen time, but the weekly screen time, right? Or is it the average? I don't remember. Let me look at it again. There's a random sample. Oh, the mean weekly screen time of the sample, though. This is the mean of the sample. So this is people reporting how many hours a week they are on their iPhones. I was going to say, I'm not in that 12 to 13 range there. I'm a little bit more than that. Right. Just as a reminder, homework is due on Thursday, not Wednesday. We will have a fire drill like right at the beginning of class tomorrow. So we'll come in. I want you to get your notes out and ready to go. And then we'll actually start the lesson once they send us back in from the fire drill.